Okay, so last topic, antimatter and quarks. This is, I mean, not that it didn't get strange in the 21st century as we're learning more about physics, but this is the most strange stuff that's been discovered. And I rarely do this in my notes, but basically the whole first slide is a story. And I don't know that I could probably leave you the cliff notes, so I'm just going to literally read off my slides. I hate doing this. You might notice I rarely, if ever, just read off my notes, but I'm going to do that one-time exception today. Story time. 1894, there's a Scottish physicist named Charles Wilson. He builds a device called a cloud chamber, and you've probably never heard of this device before, so here's a little note on it. The purpose of a cloud chamber is to simulate shadows that could be formed on cloud tops by mountain climbers. To do this, he supersaturates air inside his device with water vapor, and in doing this, he realizes that as charged particles pass through this cloud chamber, they become ionized, or they ionize some of the water molecules, causing water vapor to condense, basically turning it from a gaseous form into a liquid form. Eventually, Wilson was able to track the motion of these charged particles by looking for vapor trails. I want to do a brief aside here. You guys know how when you look in the sky and you can see the trail of an airplane behind you? That's basically what he was discovering, is that water vapor in its liquid form was water vapor in its gaseous form was being condensed into water in its liquid form, and it was doing this through charged particles, basically. The charged particles were causing ions to make this water to condense into liquid, and he could actually see a vapor trail left behind. Now, here's what he did, if I keep going here. These cloud chambers were usually operated in a magnetic field, so they could observe particles spin in a spiral pattern. Okay? And based on the direction of spin, they knew it was a positive or negative charge. You guys remember our right and left hand rules from the middle unit on magnetism, where if you had like a particle that was traveling one way, if your thumb was, say, the direction of travel, and your fingers were the magnetic field, and the force causes it to deflect one way, that's basically what he was discovering here, is that if it spun one way, it was a positive charge. If it spun the other way, it was a negative charge. And so, long story short, Charles Wilson observes this spiral. He estimates the charge-to-mass ratio, and he recognizes that the charge-to-mass ratio must be an electron. However, the spin was wrong. According to the spin was going according to a right-hand rule, but right-hand rule would be for positive charges. Long story short, he had discovered positrons. And I don't know that I discussed these a lot during one of my previous YouTube videos, but that's where we're going to go in our final section here, is the concept of antimatter. He had discovered the first proof of antimatter here. Well, let me just take it from the beginning, basically. We recognize these four particles right here as being the four fundamental particles we know of: electrons, protons, and neutrons. They were discovered by various scientists through the course of discovery in the early 20th century. The neutrino, if you didn't watch my YouTube video that involved it, the neutrino was discovered as basically being this really small particle that seemed to be lost during certain sorts of decay, like alpha and beta decay. Well, what Charles Wilson had discovered were the antiparticles, which when I try to describe these, I can't even envision them, because antimatter doesn't usually stick around for very long. Antimatter, what ends up happening is if matter and antimatter ever touch each other, they undergo annihilation, is the word we use. That's what I have at the bottom of this slide here. Particle-antiparticle annihilation always occurs whenever antimatter and matter come into contact with each other. Physicists believe that this is actually what happened in the Big Bang. They believe that there was like 10 million particles of antimatter and 10 million and one particles of matter. And basically most of them touched each other. They annihilated each other into a big form of energy, but there was just a little bit of matter left over. And that's what our universe is made out of, is the excess matter. The energy from the Big Bang, in theory, they believe came from this particle antimatter annihilation. It sounds like science fiction. Like, it really does. It sounds like this crazy, science fiction thing where, there's a positron and antiprotons. My personal favorite, an antineutron. I have no idea what makes an antineutron, honestly. Because, I get the difference between electrons and positrons. An electron is a really small particle that's negatively charged. A positron is the same size particle, only with a positive charge. But, what makes something an antineutron? Neutrons are already neutral. how do you have the opposite of a neutral charge? And yet it appears that everything in our universe seems to have a negative doppelganger. Any of you guys watch like science fiction or like DC or Marvel comics? You know how like there's Superman, but then there's like Bizarro, Superman's evil twin? That's kind of what this seems to be like, where everything in the universe has this doppelganger, but we rarely see them because they don't stick around for very long. In the 1930s, physicists gave this name to all of their new subatomic particles, and I think it's so appropriate. They called it the subatomic zoo, because they were finding all these new crazy new particles that are beyond the typical proton, neutron, electron. And there is a massive list of them. There are actually like dozens to hundreds of new like little bits of matter that are really smaller than the subatomic particles. Okay. You guys remember the idea of a quantum? How a quantum is like the fundamental smallest thing you can have? And in energy, Planck discovered that 6.63 to the minus 34 is like the smallest chunk of energy you can have. Well, physicists are trying to work on that when it comes to atoms. Okay, they used to think atoms were as small as it gets. Well, now we think that there's subatomic particles, protons, neutrons, electrons. Well, now we're thinking, well, what's smaller than that? Like, what is smaller than a proton? What's smaller than an electron? And so the subatomic zoo, as they called it, is basically all of these new fancy ideas, things like quarks. And so I've got a few slides that describe these. Before I get to that, though, I need to tell you how physicists are currently working on this. This is a picture of the super collider in Geneva, Switzerland. Anyone ever heard of the CERN, C-E-R-N, CERN super collider in Switzerland? They spent decades making this. This is one of the greatest achievements of like technology for science. This is in Switzerland, buried deep in the mountains, trying to prevent any sort of interference, basically. And there's basically these two large circles right here. And they're buried deep underground, tons and tons of concrete, trying to prevent any sort of interference. And what they do is they use powerful magnets to spin charged particles around in circles. We know that magnets can make a charged particle deflect in a circle, and they accelerate them faster and faster and faster. And so one goes in this ring here, one goes in this ring here, and when they're finally ready for them, they have them crash into each other, basically at the fastest speed possible. And what they're trying to do is basically break apart a proton or break apart an electron and see what's inside of it. For a while, there was a particle that was hypothesized by a guy named Peter Higgs. You might recognize it. It's known as the Higgs boson particle. Sometimes it was referred to as the God particle. It was big in the news a few years back because physicists found it. For years, they thought this particle should exist based on some sort of crazy math calculations. I have no idea what's going on. And then years later, they managed to smash these particles together, and they found this mysteriously small, infinitesimally small particle. And so that's basically what physicists are working on through these particle accelerators. Here's what they've discovered. You really don't need to know this, okay? I have never seen questions on this on the diploma, really, because this is so brand new and like no one gets this stuff because they're still trying to figure out what all of these little particles are. So please don't worry about trying to memorize all this chart here. Like just kind of gloss over the basics. I will show you an example of a question in a bit here as to what I have seen on the diploma on this section. So anyways, here's the basics. If you take all your fundamental particles, they've found things that they call either leptons or hadrons. And you guys can read these things here. The leptons is based on the words thin. Hadrons are based on the word thick. Okay? Basically, you're talking different sizes of particles here. There are only 6 leptons that have been discovered, whereas the hadrons, they found hundreds of these different types of little hadron particles. And hadrons, they've then broken up into mesons and baryons, which are either middle or heavy. I already talked about the Higgs boson particle. A boson particle is actually one of the expected hadron particles. Don't worry about this too much. This is kind of like their basic flow chart. Here is a table I found online that basically has a whole bunch, not all of them, but some of the subatomic particles. And as a way of describing them, we usually use the word quark. Quark is usually the word we use to describe these like tiny little bits of matter that we find after we smash particles into each other. You might recognize one of the smaller ones. An electron is actually considered to be an lepton. It's one of the bigger leptons. But there are other small particles like muons and tauons, and I have no idea what these are, and you don't really need to either, so don't stress over it. Just know that there are smaller bits of matter out there, apparently. Here's some mesons, pions, and kaons, and upsilons, and again, I don't know what they are. You might recognize that in the baryons, actually, are protons and neutrons. And yet there's other sub-pieces to that as well. So, know the main ones, protons, neutrons, and electrons. What you may find useful is recognizing that we actually use their mass in a different way. And I have a different slide talking about this, so I'd like to go find that slide right now. There is actually a chart in your periodic table. You probably haven't looked at it yet, but on the back of your periodic table, they do list a couple of particles, as well as some of the first generation fermions. They talk about positrons and antineutrinos and up and down quarks, so they do list a few of them there for you to look at. What I want to point out is mass. The way that mass is measured is not in kilograms. Okay. And the reason why is that these things are so incredibly tiny that measuring mass in kilograms is ridiculous. And so what they use instead is Einstein's formula. Remember Einstein's formula being E equals mc squared? You take that formula and you rearrange it for mass. So if you rearrange this formula for mass, you end up getting E over c squared equaling mass. And that's actually what this is measured in. Energy then is measured in electron volts, which is a very tiny unit of energy. And then you divide by the speed of light. So consider that for a second here. Energy in mega electron volts is relatively small. And if you divide by the speed of light squared, that's how you get some of these mass values here. And if you were to put them into kilograms, like you know how an electron is 911 times 10 to the minus 31? Like these are considerably smaller than that. If the electron would be to the minus 31, like electron neutrinos and tauon neutrinos, these guys right here that are really small, they're going to be to the powers of negative 40, negative 50, etc. So anyways, long story short, there's more stuff in there than just protons, neutrons, and electrons, and scientists are trying to find it. One of the problems is we have very little ability to detect it. If we could smash matter into these smallest little pieces, we can't see it because it's too small for like microscopes to pick up. Even electron microscopes, we're reaching the limits of those. So it's fairly challenging to detect most of the stuff. So this is my slide that basically describes what I was just saying. So most of these particles are only in existence for a few microseconds. They get divided into properties based on how they interact and how they spin. We cannot measure them in kilograms, so just be aware this is a new unit of mass, the mega electron volt over the speed of light squared. I don't have any practice questions for the diploma on this because I've never even seen this assessed. I don't even know how you'd assess it because this is what modern physicists are working on. So I'd ask if you have any questions, but to be honest, if you had them, I couldn't answer them anyways, which I think is cool actually. I think in most other classes, if you were to have a teacher kind of say, I don't know what I'm talking about, you might be like, why are you my teacher? Shouldn't we hire someone who knows what they're doing? I don't feel bad about not knowing this because there's probably only like 100 people in the world who really get this stuff because they work at MIT and Caltech and, those sorts of labs, right? So anyways, we cover this very superficially. If you feel like I'm glossing this over, it's because I'm glossing this over. No one knows this. So anyways. In the 1960s, physicists were getting pretty confused. They had narrowed down some of these terms I'm describing to you. Leptons were really small. Hadrons were a little bit bigger. And so they decided that maybe these things are made up of these words that I described, called quarks. And what I'd like to do is actually skip a slide here and show kind of a really cool experiment that scientists did, because I do understand this one here. I want to show you this picture here. What scientists did is they found a way to send some electrons exceptionally close to the nucleus of an atom. They basically shot the electrons, like in a Rutherford experiment. You know how the Rutherford experiment was to shoot alpha particles really close to a nucleus? They shot electrons really close to a nucleus, and they discovered these really strange results. Sometimes the electrons would bend a little bit, or they'd bend a lot. And see how these ones right here, they bent a little ways here? It gave scientists an idea that maybe matter was actually made up of subcharges. We kind of think of 1.6 times 10 to the minus 19, you know, that one elementary charge? We kind of think of that as being the smallest charge possible. But there seems to be evidence that maybe this particle right here actually has partial charges inside. That's the word we use, partial charges. And some of you may recognize this concept from chemistry. Has anybody ever seen this symbol before in chemistry? The idea of like a part of a charge, not a full proton, not a full electron, but like part of an electron. So, anyways, if you've seen this notation in chemistry before, this is a partial charge symbol. Anyways, here's what they think exists inside these particles. And again, I think the right word to use is think, because this is still being looked at. What they think is that based on this evidence right here, maybe this proton right here is actually made up of a positive 2/3 charge, a positive 2/3 charge, and a negative 1/3 charge. The reason being is that this electron right here seemed to get attracted towards the positive bit, right? If this is a positive bit right here, a negative electron would totally want to bend in towards it. But if we think that a proton is uniform throughout, and that the positiveness of the proton is everywhere, that didn't seem to fit, because it would seem that there's a negative 1/3 charge over here on this side of your proton, which is causing your electron to bend away. Consider the math right here. 2/3 plus 2/3 minus 1/3 ends up with this thing having a total charge of positive 1. This picture right here is a proton. What you would think, though, is that if the proton was uniform, and if the charge was positive 1 all the way throughout, you would expect all of these particles to bend towards it always. But what seems to happen is, on one side of the atom, the electrons bend towards, because we think there's positives on one side. And on the other side of the atom, we think there's actually a negative charge, so therefore it bends slightly away. And this seems to give rise to the evidence that there are these like subatomic particles, and they actually have like fractions of a charge. So if I can go back to this this slide right here I skipped, what you guys need to be able to do, this is one of the few tasks that I've ever seen you be assessed on, is recognize that these up and down quarks are the way that we kind of describe the parts of a proton and electron, those leptons and hadrons, those inside pieces. So an up quark is usually designated as being a positive 2/3 of a charge, and a down quark is being represented as having negative 1/3 of a charge. And so if you were to add positive 2/3 to positive 2/3 with a negative 1/3, the math, the way this works out, is 2/3 and 2/3 is 4/3. Subtract 1/3, you're left with positive 3/3. That's what we recognize as a proton. But we think the proton actually has little bits inside of it. Makes sense, doesn't it? Hasn't that been the way how science worked in general? They thought that atoms were as small as they get, and they look inside and they're like, actually, I think there's little bits inside of it. No, actually, we can go with that still, too. We still think electrons can be broken down. Yeah, this was just evidence for a proton. But really, the idea is really, what is the most fundamental particle there is? And we don't think it's an electron or a proton or a neutron anymore. We think they're smaller bits, but it's still being discovered, right? Like, this is a evolving science. So, anyways, this would then suggest that a positive 1 charge of a proton is really made up of 2 up quarks and a down quark, which is kind of what we see in this picture here. There's these pieces here. But here's the thing. Let's say that we conclusively find a way to prove these quarks right here. The next question is going to be, well, what's this thing made of? And the question after that is, what is that thing made of? You guys ever heard of string theory? String theorists are basically people who are working on this idea of trying to figure out what everything's made of, and they believe at a fundamental level everything is made of vibrating strings. I don't even understand really what's going on. Of course I don't. I don't work in that field. So maybe one of you guys will, though, which will be awesome. So, this is actually a really cool idea, then. They suggested that maybe a neutron, being neutral, is not neutral because it has no charge, but because the individual quarks inside it just happen to balance out. If we believe that you can have these positive 2/3 and 1/3 bits inside, check out how you might make a neutron. Use a positive 2/3 bit, and then use 2 negative 1/3 bits. 2/3 subtracting 2 individual 1/3, in theory, would then give you a neutron. And here's the other thing that this did then. it allowed us to explain beta decay. If you've forgotten or haven't watched my YouTube video on beta decay involved a neutron turning into an electron and a proton. Right? That's what beta decay was you have a neutron, which is a 1-0 charge, and it turned into a beta particle, which is a -1-0, and it turned into a proton, which is a 1-1 charge. This actually seems to give rise as to why beta negative decay would occur, because apparently a neutron internally has a little bit of positive charge inside of it and a little bit of negative charge inside of it. And that would explain why a neutron can turn into an electron and a proton through beta decay. So again, this is very superficial. Don't overly stress about this. But here's the explanation as of what they think would happen. If you had an up, down, down, an up, down, down would basically be your positive 2/3, your negative 1/3 bit, and your negative 1/3 bit. If you add all of that up, you'd be at 0, which we then think would be a neutron. Well, what that would mean then is if you turn a neutron into a proton, you'd then have to have a positive 2/3, a positive 2/3. Now that gets you over 1, right? So then you need to have a negative 1/3 to bring it back down to positive 1. You've now basically turned a neutron into a proton. Now what's the only difference between these two bits of matter? There's an up here and an up here, so that hasn't changed. There's a down here and there's a down here, that hasn't changed. But this down right here apparently needs to change to an up. And if you consider the difference between these two values, you'd have to change a negative 1/3 bit into a positive 2/3 bit. And in order to do that, you'd have to emit a negative 1. Because how far is it from negative 1/3 on a number line, from negative 1/3 to positive 2/3? The difference between that is a unit of 1. But for you to get into the positives from the negative, you'd have to emit an electron. And that would kind of seem to explain in a weird sort of way why it's possible for a neutron to become an electron, which is a beta particle, and a proton. Long story short, can you guys just know that matter has stuff further inside of electrons and protons? If you're good with that, that's all you need. Okay. So if you'd like to know more about this, you now know as much as I do. I am not an expert in this, clearly. So if you'd like to read your textbook, it'll talk about some of the current work that's being done on quantum chromodynamics. It sounds cool, but I doubt you're going to be assessed on it. If I could, I don't think I have it in this document. Do I? No. I'm going to find you real quick one of the diploma questions on this, just so you kind of know what they have asked in the past. And that's it. But I would not spend a lot of my time and effort trying to memorize this stuff. Unless you find it interesting. If you find it interesting, go nuts. Okay. Just gotta give me a sec to try to find that diploma they released. Here it is. Okay, so let's read through this question here together here. Number 40. It says 2 types of pions are modeled as either a down quark and an anti-up quark, or an up quark and an anti-down anti-quark. They want to figure out the charges of these. It's quite a bit to decipher. You need your table here. Okay. So find your periodic or find your data table here, because you have to know, based on your table here, the charges of anti-up, down, up, and anti-down. You just need to know what all those charges happen to be. It's on the back of your table. No, heck no. Don't memorize this. It's kind of a silly little puzzle. I don't even know why they expect you to memorize or know this stuff here. But look at this one here. Find a down quark on your table. What is the charge of a down quark on your table? Negative 1/3. And it seems to also involve an anti-up quark. Remember how we talked about how there's that antimatter out there? So if you read on your list here, apparently an anti-up quark has a negative 2/3 charge. So if the down quark is a negative 1/3 and an anti-up quark is a negative 2/3, add negative 1/3 and negative 2/3 together, what would you get? Negative 1. So it would appear that it's got to be either C or D. The first particle has a net inside of it of -1, which basically suggests that electrons are made up of like little bits of stuff. The other one is an up quark. If you read on here, an up quark is positive 2/3. A anti-down quark is positive 1/3. So positive 2/3 and positive 1/3 would give you +1. So apparently the answer to this one was C. You guys feel like you could follow that? All you had to do is basically just read this little chart here, figure out what charges there were, and just add them together. So if I didn't do a great job of explaining that, the down and the anti-up, when you add the charges off your table together, this and this added up to -1. This and this added up to +1, so that's why the answer was -1 and +1. Okay. Let me find you one more released item they've shown in the past here. There's usually one question on this, and it usually just involves you having to use the information they give you there. It says a neutron and a proton can be modeled using quark combinations. You got to figure out which one of these rows correctly matches how you'd make a neutron and a proton. So just kind of walk through them one at a time. If you had an up, down, down, look on your sheet here. An up, down, down would be a positive 2/3. And then if you had two downs, that would be two -1/3. So an up, down, down would have a charge of nothing. Hey, that's what a neutron should have. So UDD would work. Okay. See how there's a line on top of these ones right here? That line refers to the antimatter ones. So if you were to look at the antimatter ones, this would be an anti-up and two anti-downs. That would be, okay, where's anti-up? Anti-up is -2/3. And then two anti-downs would be two of those ones right there. That would also give you a charge of 1, but it wouldn't be considered a neutron anymore. This would be an anti-neutron. Does that make sense why C and D would be out? Because in this case right here, you've made the neutron. In this case right here, you've made the anti-neutron, even though the net charge is still 0. So it's got to be one of these last two right here, right? So let's look at the charges on a proton. To make a proton, if you have two ups and a down, that'll do it, yeah. Two ups and a down would get you the charge you need for a proton. These ones down here, probably for antiprotons. I'm guessing that if you use two anti-ups and a down, or an up and two anti-downs, you might get like antiprotons or anti-electrons or positrons. So all you've got to basically do is just check out the charges there, but it definitely can't be C or D though, because that would give you antimatter, not regular matter. So hopefully I explained that well enough, all you got to be able to do is add some fractions in your head. If you can handle that, you know what you need to know. So. Did that make some sense? So, quick summary of what we learned today, which I feel very inadequate teaching you, but that's okay. I've got to peace with that. All you need to be aware of is that this is what we believe is actually inside of protons, neutrons, and electrons. We believe that there is little tiny bits inside there. Some of them are positive, some of them are negative, some of them are partial charges. I bet you one day we're going to discover that they're not even in 1/3 and 2/3. There might be like 4/17 of a positive charge and -3/19 of a negative charge, right? Like one day we're going to discover all these like partial little numbers inside of there. But as long as you can add them up to become protons, neutrons, and electrons, or use the negative antimatter to find those, that's really all you need to know. So, sound good? Sure. Okay. No one's reacting.